be trying to go over some of the basics of how to use SPARTA and things like that, something you guys hopefully find very useful for your projects. I try to post some key links. I'll go through a lot of the basics, and hopefully at the end we'll have time where if some of you have questions about your specific problem, how that could be simulated in SPARTA, might be able to go over that. One thing also is I do have your graded exams, so at the end of class, please come up and I can give them back to you. Thank you. So, to get SPARTA, it's a DSMC code that we'll be using, or at least that I'll be showing you how to use, so it's recommended you guys use this. Certainly if you find other ones, there are other open source ones out there, you can use those as well. So everything about SPARTA you need to know is on this website to download it, and I've done some of this for you already and it's posted on Piazza, but now download, you click SPARTA, download here, you get a nice big tar file, posted that file on Piazza. Then also, nice thing to see is the manual. This is, especially if you try to do some more complicated things in SPARTA and like try to see just the basic syntax, it's all in here. It's all very well described for open source code. It's a very big manual. You can see it's like, I don't remember how many pages, but quite a few. Everything's very well described, but I'll try to show you some of the basics and also how to go through the manual and things like that. So one thing I want to first show is, and I just made a post of this on Piazza this morning and pinned it to the top, so hopefully you can all find this easily, but some basic commands for cluster and how to use SPARTA, things like that. So this should all be there for you. As I come up with more commands and stuff, I might be adding to this. If you have any questions, feel free to either comment on this. I should have given you all comment permission, or post more, or post questions in the Piazza thread. So now for the cluster use, we're all given a computational resource called Scholar. So this is some time on the cluster. So if you have like either some sort of Unix command, then you can log on to that and you're more experienced, that's good. But I'll be showing how to do it in case you have no experience or just don't want to deal with that. Best way is if you just Google Purdue Scholar, RCAC, something like that, you'll run into this website here. And there are sort of three options for what you can launch. One, I'll go first this one. Sorry, log in. So here, this is kind of all the files you have on Scholar. For you guys, it'll probably be blank to start off. But the nice thing here is it's easy to download the files and also upload. You know, you can upload, and if I select, can't download a folder, but if you want to download the entire folder, you can zip it and then download that file and upload it. You know, just click here, upload whatever file you want. So taking files on and off the cluster through this is pretty easy. There's other ways to do it through a more professional way, but this is good enough. And the other one that I'll use, there's a third one here that I think seems pretty nice and tries to combine the two, but I'm more familiar with this one, so I'll just stick with this. It still gives you kind of this sort of terminal link, so this is just all through the website, so it's all really easy. I guess starting off with logging on. To log on to SPARTA, should have the command. If not, then I'll put it up there. Yeah, so just SSH your username, then scholar.rcac.purdue.edu. This might ask you for your password, although here you're already logged on, so it shouldn't. It'll take you into Scholar. And now I'm kind of on the place where I can try to access these computational resources. Few things to note, so and I try to give decent list here. So a few things, like one thing I say, and I say do this right after logging in, load the modules. Basically, to interact, to run some of the commands, you need some of these modules. So let's quickly do that. GCC and module load OpenMPI. You know, it might not help you, it might not affect you, but basically if you don't have those and some of the commands to compile SPARTA, things like that, it won't let you do it, and it'll come up with an error. Usually the error is always this. It always is the case for me. One thing to note is when running this sort of Unix environment, there's a lot of basic commands, ls, cd, things like that. I won't go over all those because those are pretty basic, and if I went over every one of those, I'll have too many lectures. So if you need help with those, you can look up Unix basic commands, things like that. You should find a bunch of resources online. I'll try going over more of the things that are specific to this cluster and using SPARTA. So that tar file that I uploaded or that you download is kind of the entire SPARTA directory. It's that one specifically. So either you can download it, or you download it from the website or download it from Piazza, and then upload it here, just like through this Jupyter thing works. And then to untar it, there's put this command here. So you just have that, and then you'll untar it into the folder that I just in here. One good idea with SPARTA is it has a very nice kind of, not only is it friendly in terms of documentation, but also in terms of the platform here and all the directories, and gives you a bunch of examples and things. So it's a good idea, I think, to spend like 30 minutes or so just getting familiar with what's in here. You know, you have your bunch of example cases, which is good to reference to start off your input files. The source code, if you for some reason want to mess around with that. The tools, which actually hopefully I'll get to today. And various things like that. So definitely a good idea to try to get familiar with what's in there. To compile, and you don't have to do this because I did compile it and upload it on Piazza, so you should be able to just download that, upload that onto Scholar, and then run with that. But if you want to compile it yourself, or for some reason that's not working, you go into the source directory, and then just make MPI, and then it, well, the reason it did is just because I already have a compilable file here, but if I didn't, it would compile it all. And again, if I, let's say, didn't have the module, I'd get some sort of error. So that's why you always want to load the modules right away. I think that's the basic now. I think I can get more into using SPARTA. So I have a few cases that sort of from my past research that I've uploaded these into Piazza as well. So I'll try to go over that, because I think those the example cases they give are very simple, so they're good to start off with, but I want to give a more complicated, more realistic case that at least I used myself, so it probably will be useful to you. So this is kind of the input files. So the way, SPARTA, they give you all your source code and everything, you compile it, and then you just need this input file to characterize the problem, to tell it specifically what you want to simulate. If you remember last time, the slides I presented, at the end there, and I didn't have time to go through those, but there are a lot of kind of examples, I believe 2 different ones, and they went through pretty good depth of the input file, so you have that as well to guide you. But here's some more help, and I'm going to try to go point out a few key lines here that are important for you to know. So one thing, first start off, the dimension of the problem, it's either 2 or 3. If you have a 1D problem, then usually you just make it 2 and set your boundary conditions such that the problem would be a 1D problem. The grid doesn't really change between a 2 and a 3D. That's kind of one nice thing I think about SPARTA. It still keeps a 3-dimensional grid. It's just if you have a 2D problem in the Z direction, you should just make one cell and make the boundary conditions appropriate like that. So yeah, you have this dimension 2 boundary. This is where you specify the boundary conditions. The basics are the outflow boundary O, R reflective, S for surface, P for periodic, and I should show, again, like I said, the manual is really good. They should be all in here. Oh, here we go. Let's just find a PDF file. There we go. There's that loads. Okay, here we go. So here, and it gives you not only all this thing, but all these, every single command you could use in SPARTA are detailed in here. So if I look at the boundary command, so here I see kind of the syntax, how to use it, and then all of my options, some examples, and then description. And in this case, it's only 1 page. For the more complicated examples, it could be 10 pages or more. So it's a very nice resource, and certainly I don't have to repeat all of everything in here. So yeah, so here boundary, specify what you want your boundary of the domain to be. Create box, this is you actually saying that how big you want your simulation domain to be. So it's saying, in this case, I want my box extend, in the x direction from this dimension to that dimension, from the y here to here. And for the z, if it's a 2D problem, you just make it a negative 0.5 to 0.5. 3D problem, you change it to something you actually want. Create grid. If you remember in DSMC, you discretize the domain into these cells. So that's what we're doing here. We're saying that I have 50 cells in the x and y, and just one cell in the z, which again is required for a 2D problem. So I can't really see. Sorry, here we go. This command, I remember looking up in the past what it did. I don't really remember, but I just have it in there. So I suggest you guys do too. Global is kind of a command generally done for basically parameters that you think of as global to DSMC. So number density, and then FNUM. If you remember what FNUM is, that's your ratio of computational particles to real particles. Then we start getting into some of the more details of our flow. So thing here, and for you guys, in many cases, it'll probably be a much more simple thing, but you specify what kind of molecules you have and how many of each molecule do you have. So here I say that I have 5 different species, N2, O2, NO, and NO, and that the details are all given in this air.species file, which I'll try to show you later. Then I say, again, all these species are going to be traveling with a stream velocity, and here I specify what the velocity is and what the free stream temperature is. One key thing to note is that you need to keep the order here the same, or else, I don't know what happens, somehow it really messes up the results. So just keep these the same. And then mixture, then here I'm specifying my concentration of each species. So here I'm saying 75% nitrogen, 7% oxygen, so on and on. And that's how much, again, is in the free stream. So this is what will be flowing into the domain. Then in most cases, you have a surface or something will be flowing around. This is a re-entry problem. So I had a CubeSat flowing around. That was my problem here. So that is read surf, and then I give the coordinates here, or kind of the details of the surface. Then after that, you have to specify what happens with the particles that collide with the surface. So you say, so I'm saying that they collide all surfaces, and then if you remember, I believe either I've talked about or probably Professor Alexenko, but there's different types of collisions, specular and diffuse collisions. So if you just say specular here, and then I remember all the details, they're all given again in the manual. If you do surf collide, you'll find that. But here in the case of diffuse, which is probably what you'll be running with, since that's nothing, no surface is specular. So you say diffuse, then you say the temperature of the surface and the condensation coefficient. If you're running condensation coefficient, if it's 0, it's basically a specular collision or a specular surface. If it's 1, that means it's perfectly diffuse, and more realistic number is 9.9. So it's usually it's 90% diffuse. And then this is saying that the surface is going to be at 300 Kelvin. And then this is just saying, all particles that collide with the surface collide according to my ID number, which is called 1, and that's the ID here. So SPARTA in this input file sort of runs with these ID numbers. And if you look through enough commands within the manual, you'll catch on that. Global surf push yes, that just forces the surface to all be watertight. And naturally, with some cases, how your surface might be cut up and everything, you might have a kind of some gaps naturally, some very small gaps. So this just forces everything together to make sure particles don't leak in. Here we have to talk about what happens when particles collide with other particles. So this is a VSS model. You guys know hard sphere, VHS, VSS. And basically in SPARTA, everything by default is VSS. Better just keep it that way. By saying this one, collide, modify, vibrate, smooth, this is activating the vibrational mode of energy. Naturally, it's not activated. That's kind of one thing SPARTA added more recently was a vibrational mode. So you have to specify in here, which for lower enthalpy flows isn't really important, probably actually not worth doing even. But in this case, being a re-entry problem, vibrational energy is huge. So that's why we have to do that. Then I say reactions, depending on the problem, you might have reactions. So here I'm saying it'll react according to what's specified here in air.tce. By the way, stuff that has a number sign, that means commented out. In this case, this is commented out, but I'm going to uncomment it. Create particles. So if I don't have this command, that means I'm starting with my domain in vacuum, which is OK, but I generally don't like to do that. I always like to populate to start off. So I say create particles, then air. Again, that's the name of my species here. I call this mixture air. So that's what it is referencing here. So it's saying air and then number of particles, and then the number here. So strangely enough, if you put 0 particles, it actually doesn't put in 0. It puts in the number that would calculate according to your number density, fnum, things like that. So it puts, yeah.
So create particles, that command actually is your initial condition at the beginning.
This is how I'm populating the particles in the domain. So if I don't have that, that means I don't have any particles in.
At t equals 0.
T equals 0, yeah.
Okay.
And if a particle leaves, a new one appears.
Well, that depends on your flow from there.
Okay, yeah. Okay,
Yeah.
Yeah.
But so this is just starting off, and the thing with starting off, it's not going to start off with anything realistic. It's start off, it samples all the particles for these locations and the internal velocities and temperatures according to the distribution function. And certainly in this case, reentry flow, those will be way off it'll be much colder to start, so I need to give it some time to basically form a more realistic solution. But I generally like to just put this in to get started. Yeah. And then I have, okay, so this one is a bit of a strange command. So before this, we haven't actually told SPARTA where particles are coming from outside the domain. So we can tell it that, oh, you flow out, that you reflect off the boundaries, that you want to collide with the boundaries in a certain way, things like that. But we still need to actually emit particles, most likely. I mean, it depends on your specific problem, but almost all problems need this. So here you say fix, then emit/face, then air. So this is, again, emitting things according to what's specified here. And then I'm telling it which faces. So the lower x boundary, the lower y boundary, and the higher y boundary. And for a 2D problem, you can't do z, but in a 3D problem, you probably would have z a lower or higher in here as well. So yeah, so to answer your question, when you asked if a new particle appears after an old one leaves, that really depends. You might have you might be naturally losing particles in your problem. You might be naturally gaining new particles. So yeah, I guess I can't really answer that question generically. Time step, if you remember how to calculate time step, we went over that last time, and then you put that in here. And then here is the thing. Now we are, so we're done specifying the problem. Now we're trying to get more computational advantages, or I guess not computational advantage. Some of it is diagnostics. So when SPARTA runs, in this case we're saying stats to output tell us what's going on every 100 steps. Just a generic, basically how is everything running. So every 100 steps, then every 100 is going to tell us the step number, the CPU time, number of particles in the domain, number of attempted collisions, number of collisions, and so on and on. You can again see all the options in the manual. It's a very good tool to just see. You can't really tell anything about your actual problem, but you can see if something's going drastically wrong. So that's good for that. So then the next thing is a bit of a, strange, not necessarily so intuitive, but I like to do this, is kind of when you start off your problem, naturally things are not yet realistic conditions. Either you start off with a complete vacuum, or you started off with some particles that aren't representative of the actual flow. So what I do is I call this unsteady flow. So I initialize the problem by basically running the simulation before I'm taking any data, just to make sure that things are set properly before I start taking the data, taking the samples. So this command here, I'm not going to go too specifically what it does, but basically for this sort of flow regime, which is still unsteady, you want to use this command. Later we'll change it to something else that's better for the steady flow. Then I'm telling it you run for 5,000 time steps. And then the next thing, and this is really dependent on your problem. If you have a hypersonic problem or something where your flow will vary drastically, or like a ramp plume kind of problem, so your flow, your density might be very large in one place and very small in another place. You want an adaptive grid. So what that's going to do is that's going to make your mesh finer in those places where the flow is very dense. It's like in a hypersonic flow, you have a shock wave there, so you want like a lot of cells to really capture the shock there. But behind your vehicle, you'll have a wake, so that's not as dense flow, and you probably aren't as interested in that realm. So in this case, what we're saying is we're going to adapt the grid every 20 steps, and we're going to refine and coarsen according to the number of particles in the cell. And if there's more than 45 particles per cell, we're going to split the cell. If there's less than 15, we'll refine. Well, this is a nice tool, but it's kind of, I guess, not a perfect thing. It's sort of limited what it can do. It's tries to split the cells, one cell, refine and coarsen, combine with a bunch of other cells. So you can't really rely on this to do everything perfectly, but certainly does help the problem a lot.
Sorry, I
Yeah.
think I missed it. What does 20 mean there?
Every 20 steps, you start refining.
Okay.
Yeah, that's what that means.
But you don't say how.
Don't say how. You mean what criteria I'm using to refine the mesh?
Like, how are you going to determine the new size of the grids?
So it can't do it. Basically, it automatically does it, and it just has to do it according to other surrounding cells. So it tries to merge the cells. If it splits, I believe it just splits it in half.
Okay.
So it's yeah. So it's kind of limited in that sense, but it's still better than nothing. And certainly the nice thing with this is you can start off. If I go back to my create grid here, this is my level 1 mesh, 50 by 50. That's pretty coarse, but that's okay because I have this coarse mesh to start off, and then I'm refining it to make it much finer. Also, one thing to note is your level 1 is as coarse as the mesh will go. So you can specify level 2 and level 3 mesh to make it finer, maybe give your mesh more flexibility. Yeah. Then I'm saying, run for another 10,000 time steps, and this lets it basically run or refine the mesh, and that way get a more optimized mesh for the problem. And then let's do unfix. Basically, this is saying I undo or delete this command. So now afterwards, I don't want it to continue on. So that's what I'm doing there. And then remember I said this collide modify that was up here. I said that was good for the unsteady realm. Now here, this is what you use for, now that we're in steady, you use this here. And these commands, okay, so these get a bit more complicated, but I guess they're necessary because ultimately you want to see what's going on with your flow, right? So after you run this, you want to see what your results are. So there are kind of two things to compute in DSMC for this. You compute the kind of your grid properties, so your flow field properties, and that's what makes the nice flow fields to plot and everything. And then you compute the surface properties. So if you're interested in your drag on your vehicle specifically, that's where it comes in. So I guess I'll have to go through this quickly, and this is something really good to reference the manual, since there's a bunch of kind of small syntax things which I always mess up many times in before I finally get it. So it's really have to go through the manual to make sure you're doing it right. But this one's compute, so every time step I'm going to be computing some properties here. Then I call my compute ID C1 grid. Then I say I'm computing grid, so this is the flow field property. All means I believe I'm going over all cells. Air, so I'm computing for the mixture air. And then I'm saying here, so this is numbered, and the variables number of particles per cell. This is good just to indicate, make sure you don't have 5 particles per cell somewhere, that you have 10 or more particles per cell consistently. Number density, X component velocity, Y component velocity, rotational temperature, vibrational temperature. Weird thing with SPARTA is that they implemented this translational temperature and pressure a bit late. So instead of putting in here, they introduced this new command that's specifically for, basically all it does is compute translational temperature and pressure. So you want to include this command here. This one, it might tell you that it's computing. It gives you the option to compute translational and vibrational temperature in this command here. But actually, there's something wrong with the calculation. And at least last I know, they just decided to start this new command. So just use that. Next, so here we just computed, and we're computing every time step. So we're not really getting a good set of properties because things obviously vary from one time step to another very greatly. So what you want to do is you want to average over a greater number of time steps, which is this fix command. So this fix will average our computes, and this is, so these three numbers are a bit confusing. So this is saying I'm going to perform kind of the averaging over this many steps, 10,000 steps. Then here it's going to be the last number of steps within that first. So basically the last 10,000 steps within every 10,000 steps. And this is how often I'm repeating it. So one step. So the example that they give is for these numbers would be 10, 100, 1,000. So if it was that, it would be every 1,000 steps I'm going to repeat my fix command. For 1,000 steps, I have the last 100 steps. And for the last 100 steps, so basically for step number 901 to 1,000, and then that I'm repeating the frequency every 10 steps. So it'll be 901, 911, 921, so on and on until I get to, or maybe it's starts at 900, whichever way it starts. But it continues that. Personally, I don't really get the point of reducing it, so I just do 1, 10,000, 10,000 like that. That way I'm repeating over enough steps. So 10,000 steps is most cases enough to get a pretty good sample and not have noise. And I'm repeating over every step. I'm going to ignore this command because you probably aren't interested in it, but this one lets you, if you're interested in a specific mean-free path or Knudsen number or something locally, this will give you that. Generally, I haven't found it too useful. Then after you compute it, this command comes in where you actually need to dump the file so that you can actually see it, plot it, things like that. So here I'm saying dumping every. So here I'm doing every. One thing I should mention about this fix command is then you have to average, and either you can average over single steps, so basically one time, or have a running average. In most cases, a running average is better, but depending, sometimes you just want a single output. So this will be one or running for that. Now for this dump command, so here we're actually outputting our results that we just computed. So here I'm outputting the frequency every 100,000 steps. I found that it's, for some reason, better to do something that's greater than, but still a multiple of this number. If I do it equal, sometimes SPARTA outputs just a bunch of zeros. Not too sure why. So it's better to do it this greater number here. Then I'm saying the file name. I'm outputting here. This asterisk means that it's going to be the step number. And then I'm outputting my coordinates, so my x and y coordinates of each cell. And then here I'm saying I'm outputting a fix command with this ID, which is this fix command here. Next. Oh.
So you're not outputting all the things that you're calculating in the second step? Like n number density?
Okay, so, sorry, yeah. So this computes it for every time step. This right here, I should have mentioned this. This is averaging, and the computes as calculated according to here. So this fix command averages all of these two. So yeah, I am outputting that, I guess, with this. Next, this command is similar. It's just done for individual species. So if for some reason you want to look at what in this case, I have 5 species. If you're interested in saying something about that, you get the exact same, but just with individual species here. And then the surface. Surface kind of works similarly. Yeah, so you still have your computes. You compute all these properties you want on each surface. Still fixing it the same way for grid, and then dumping the same way. Only here, count with surface, you have more coordinates to output because you want your vertices of both. The way SPARTA breaks it up is for 2D surfaces. I have 2 coordinates, to start. Every part of the surface is a line, right? So it breaks it up into panels. So I have basically my XY coordinates of one point and my XY coordinate of the other point of the surface. For a 3D problem, it forms triangles. So you actually have 3 coordinates for each point, and you have 3 of those points. And then we'd have v1x, v1y, v1z, v2x, v2y, and so on so we have a total of 9 points here. And then finally, I'm running here. So I just say run for 200,000 time steps, and then after this run's finally done, and I have something to look at. All right, well, I guess I went through that input file. Any questions about that? Yeah.
I'm not sure if you mentioned it or not, but where do you define your reactions?
Reactions are defined. So here it says react according to the TCE model, total collision energy, and the details are defined in this air.tce file, which is what we'll look at coming up. So basically in terms of the reactions, unless you're really looking to change the reaction rates, they're a problem which I think would be a very big problem to do for this project. You just copy this air.tce file into your directory, and yeah, you just stick with this file would be my suggestion. Let's see. So now I want to go through and show those a few other files that I reference in this input file. So one nice thing about this bar is there's this examples folder. It gives you a bunch of very basic cases, but still something nice to build off of. So one I like to often build off of is circle. First I want to see, so remember the surface file that's needed. Here's this data.circle file, which is so this is a file of a 2D circle, and its output here just breaks up into all your points and then lines, and the lines are just telling you how you connect your points. I'll hopefully have time to show you how to how to create some of these surfaces. But one thing, if you remember the species file air.species that we referenced earlier, that's all shown here. So here I have the names of all these species, O2, N2, so on. The molecular weight, the molar mass, then rotational degree of freedom, and you have all these things here. Basically, unless you want to add new species, you can just stick with what's in this file. If you want to add new species, then you have to add each one of these. Then there's the VSS file. This is according to the collision model. And that the important thing here is your diameter, your viscosity coefficient, and well, here they have the reference temperature, which is again important for the viscosity coefficient, and your alpha. And that's again specified all here. So as long as you're just using these molecules, you have nothing else to worry about. You can just keep using these files. So this case example doesn't have chemistry, but they have an example called chem that does. Air.tce. And this right here shows you all these reactions possibilities, and then shows according to the reaction rates here. I don't remember what every one of these means. Let's see if I can. It's saying it's a diffuse collision. Is a D. A, I believe, means it's going through Arrhenius rate, if I remember correctly. Then I don't remember what all the numbers afterwards are. It should be specified in the manual, though.
Did they specify reaction energy?
Yeah, definitely. And then E is exchange reactions. I is ionization. Unless you're dealing with some really exotic problems, you shouldn't have to deal with this. And then there is, oh, maybe it's not given in here. There's another form, recombination, which I guess aren't given in the examples. So I guess if you want to add some sort of recombination chemistry in here, then you'd have to do a lot of work to figure out what these rates are. I guess with it not being in there, my suggestion would be try not to do that. Okay, well, I think I went basics of SPARTA. Now I want to, okay, one thing I want to show you quickly before I dive into how to run it is how to create some of these surface files. So you can, luckily SPARTA has in this tools directory here, has some basic kind of tools to help you create some very basic surfaces, just rectangles, circles, and 3D boxes and spheres. So very basic stuff, but still something good to get you started. I have some of the basic commands here, explaining it. So you do, go to the tools directory, export, type in this command. Note that you have to make sure the path is the same. So on all these, whenever my username, whenever you need a username, I just have mine, so you need to change that out. So I just copy this command in. Oh, I guess it doesn't want to copy. Well, type in this command then. Doesn't want to copy into there. Then, let's see. If this is, so surf create.py is not executable, so you have to do mode 755 surf create. Then it becomes an executable file. And then you can run it with according to, I run the surf create. And luckily this is really well explained, so I'm actually going to just go straight look at that file. So here they have a bunch of comments, which I'm not sure how well you can see. But here they tell you all the possibilities of what you can do with this. So if you want to create some of your own surfaces, go to this file and check that out. I give an example here of creating just a 2D rectangle. So I say, my file name is coldbody.dat, rectangle, and then I give the coordinates of the rectangle and the number of panels in the X and Y direction. And that's really well explained there. So, all right, so now some basics of how to run. One other thing before I get to that is if you're doing some sort of atmospheric measurements, basically a question could be kind of what should be your composition if you're getting to a reentry problem or anything high altitude wise. You might ask what kind of composition is realistic. So you look up this NASA MSIS E90 atmospheric model, and here you can choose all this information, year, date, hour, things like that. Then you choose what you want to output, which information, which is usually you want here. So these, and then I submit that. And now I'm getting kind of for all the altitudes I listed, I get all these densities here. One thing to know is these are in cubic centimeters, not cubic meters, so make sure your conversions are correct. But yeah, so this is a really nice tool if you want to come up with some good, realistic compositions, because these are actually data measurements that were taken. And it goes up to, I'm not sure if 2017 data is on here yet, but 2016 certainly is, so it's a very good source there. All right, still have a bit of time. So I want to see if I can run some basic cases. Okay, yeah, so I'm just going to run the circle case view, and I tried listing all the commands here. So QList is viewing your computational resources. So once you log in here, so everybody should look like this, where you have access to this debug queue, long queue, and Scholar. This tells you the amount of resources available and what's free. And this tells you how long you could run cases. So debug is only 30 minutes. You really only have very short cases to run there. Scholar is the one that's going to be generally recommended, but it's still only 4 hours. So you have to keep generally more simple cases. And the long is if you want, obviously, some of these longer cases because you have a 72-hour wall time. But the issue here is that with Scholar, it's I'm not sure. Basically, they have to prioritize. The cluster system has to prioritize and schedule all the jobs. So with this, you might be stuck in the queue for a while. So you want to get started on this super early, and don't expect your jobs to finish if you're going finals week. So please get started like really soon. Let's see. One thing is, if you want to view the status of kind of what your jobs are, if I do qstat-u, then your username, it'll tell you the status. I don't have any jobs running, therefore I clearly don't. I have nothing. But if you, I guess I'll try to submit a job and see if I can view it. One other nice thing to do before you submit a job onto the clusters is submit it on the front end just to make sure that everything's going to run properly. If you have a small syntax error and you submit on the cluster, it could take you hours to find out that you messed up, and you might not check until the next day, and it's just like a small syntax issue. So my executable file is SPA.mpi. My input file is going to be in.circle. So if I'm just running this, pi, so this is telling it to execute the file, and the input file is in.circle. I run that, and then here it's running. So, and it ran and completed. So I know this file is good to go. One thing I did is make a specific file that should crash to show you a bit of that. So here it's telling you that, okay, SPA in.circle underscore wrong, and then it says, oh, the z dimension must be periodic for 2D simulations. So that means I have to go into my file and I see, oh, well, I made this outflow. So I change that to periodic, then I won't have that error. I believe I have an error elsewhere. Yeah, and then it tells you. So it tries to give some very specific comments. And if not, then, well, worst case scenario, then in the manual, there's a long list of possible errors. A lot of them, unfortunately, are just going to be self-explanatory because sometimes they really just tell you what the error is. So if that's the kind of comment they give you, then you should go to the specific create grid command and see what's wrong. But it does tell you. So the number, the z value must be 1 for 2D simulation. So here I have as 2. Oh, sorry. Here. I believe I messed something else up. Yeah. And basically illegal. And this one is much more generic, right? It doesn't tell you specifically what's wrong. It just says illegal surf collide diffuse command. So this one doesn't tell you what's wrong. So you have to sort of look at the file and probably look at the manual at that point to see the syntax and sort of line it up. So it's all kind of out there, well explained, but we'll still take a bit of digging. But if you have that, to actually submit a command, or submit a file to run, you need this PBS script, which is also on Piazza. So what this is, and boy, the coloring scheme certainly does not help you guys here. Okay, well, I think I uploaded a more updated one than this. I made some changes. So look at it, but basically you're telling it to run in the queue, in the specific queue you want, which should be Scholar or Long or Debug for you guys. Your wall time, you're limited by the wall time, so you can't submit anything over that max wall time they give you. Then you have to say how many you're running on. Generally just nodes one node and 20 processors. I believe Scholar should also have 20 processors, so you want to keep that in. Yeah, then there's module load, just like I told you, module load, GCC, module load, OpenMPI. Here I only have OpenMPI for some reason. The one I uploaded on Piazza is more updated than this. But that is, so you have that same here, and then you run the file, just like kind of we did here. So we did SPA, MPI, and then our input file. This is telling it to run the same way, just on the cluster now. And then the way to submit that, is just Q sub 125. Submit that, and then in this case I have a outdated queue, but so that's what the error is. So if I update that, say I want to run on Scholar. So now it says it's running. Then I look at qstat-u, because what I told you earlier, I can see. So this job, the job ID, and then my number of nodes, number of processors, and the required time, and this is Q. And when it's running, it'll say R. If you catch it in the seconds after it completed, it'll say C. But soon after that, it'll not be shown here. So, and also if I look at Q list now, because I'm running in Scholar, I guess this job might have already. Yeah, so it says completed. So I guess the case, but I didn't have the necessary files in here, so it actually crashed right away. But here, if I resubmit right now and look at queue list, so now I see here, Scholar, there's 20 cores in the queue. Those are 20 I'm using. Yeah.
Are you using all 20, or is it just using one process?
All 20 with all 20, because in that file I specify one node, 20 processors per node.
Okay. But is your code running in parallel?
Yeah, Sparta is very parallel. It's parallelized very well, so you definitely want to use all 20 in one node. There's only a few minutes left. One thing which I didn't get to today, try to see if there's any resource I can post. But once you have that file, so have the kind of the flow field files, basically the question then what to do with them, and you want to somehow plot them. We suggest TechPlot. I believe Israel's PowerPoints are the ones I showed you last time. I believe those go through and explain that process. I'll have to see, and if not, then I'll make a post about on Piazza how to do that properly. Maybe I'll come in for like 10 minutes or so and show you guys quickly, but otherwise, yes, I think that'll be best way. I guess, are there any other questions? Yeah.
So I saw that you were coarsening and refining your grid based on number of particles. Is there like a number where we can be confident where our results aren't being affected by how we're refining our grid? Like if our grid is too small, or
generally, so in this case, and the reason I like just to go by a number of particles is because kind of there's the rule of thumb in in DSMC. If you want at least 20 particles per cell, that's actually more strict. It's usually 10 is the bare minimum. So basically, if you see that your cells are too small, where in some cells you're having less than 10 particles per cell, then you know that there's something wrong with the refining process. And it might just be that, in this case, I specify that my cutoff is 15, right? If I have less than 15, I coarsen. But it might be that it's not able to coarsen because basically you have one small cell squished between a bunch of bigger cells. So then in that case, you might want to raise that lower limit from 15 to 20, things like that. That's basically the best guideline based on number of particles per cell. Anything else? Anything that you guys want to ask about maybe your specific problem that I could give tips on how to do this in Sparta?
Is the grid always like Cartesian?
Yeah. Everything is always Cartesian. One thing, I guess, so I should say, there's a possible of an axisymmetric simulation, which is just a rotational, so it's like a 2D problem, but it's a simulated large cylinder instead of a large box. In that case, I guess my first recommendation would be you want to try, before you get to axisymmetric, you want to start with just a 2D case of that with your boundary instead of axisymmetric being a symmetrical boundary. Make sure that looks okay. And there's reasons to do axisymmetric, but just in the way SPARTA works, you have to play around with a few other commands. There's one in here. I'll try to run through those, show those quickly. So there's wait cell. Sorry, where is it? Oh, okay, here. So in the global command, there's, after you say that you want axisymmetric, you have wait cell by radius. And this is telling you in the axis case. Otherwise, you'll have too many particles on the outside of the domain, not enough close to your close to the center. So by weighting the cell by the radius, you're telling it to kind of even out that distribution better than it would naturally. And then also the FNUM isn't as clearly defined in an axisymmetric case as it is in the 2D case, so you have to play around with that a lot more. So always my suggestion is first just make a 2D, make sure that looks better or good, and then you can start trying to play around with the axisymmetric. Well, I guess that's it. So thanks a lot, and again, come up to